Hello everyone. Today we're diving into kinetics of rigid bodies. This fundamental area of study helps us understand how forces and moments affect the motion of solid objects that don't deform under normal conditions. In this introductory slide, let's understand what kinetics of rigid bodies really means. Think of it as the study that connects forces and torques to the resulting motion in rigid objects. Unlike kinematics, which only describes motion, kinetics explains why and how that motion occurs. We'll be exploring both translational motion, like a car moving forward, and rotational motion, like a wheel spinning. The beautiful thing about this field is how it brings together Newton's laws, energy principles, and momentum concepts into one unified framework. Now, we're getting into the heart of our topic, the equations that govern rigid body motion. These equations are like the rule book that nature follows. When we study rigid body motion, we need to consider both linear and angular components. The equations we'll encounter help us predict exactly how an object will move when subjected to various forces and torques. Remember, these equations are built upon Newton's laws, but extended to handle more complex scenarios. Let's focus on translatory motion, when all points in a rigid body move along parallel paths. The most fundamental equation here is Newton's second law, F equals ma, where F is the net force, m is the mass, and is the acceleration. What makes this special for rigid bodies is that we can treat the entire object as if all its mass were concentrated at the center of mass. This simplification is incredibly powerful and makes many complex problems more manageable. In this slide, we're examining what makes translatory motion unique. Imagine a train moving on a straight track. Every part of the train moves with the same velocity and acceleration. The key point here is that during pure translation, there's no rotation involved. Forces acting through the center of mass cause pure translation, which is why we often simplify our analysis by considering forces acting at this point. Let's talk about fixed axis rotation. When a rigid body rotates around a stationary axis, all points on the body follow circular paths around that axis. This concept is crucial in understanding the dynamics of rotating bodies. The equation for rotational dynamics is represented as torque equals the moment of inertia times the angular acceleration. In this equation, torque, tau, represents the rotational force applied about the axis of rotation. Moment of inertia, I, is the measure of the body's resistance to changes in its rotational motion. Angular acceleration, alpha, is the rate of change of angular velocity. Understanding this principle helps us analyze the motion of rotating objects, such as wheels, gears, and any system where rotation around a fixed axis occurs. Let's explore the moment of inertia. When a rigid body rotates around a stationary axis, all points on the body follow circular paths around that axis. The moment of inertia measures the body's resistance to changes in its rotational motion. It's calculated as the integral of the distance squared from the axis of rotation times the mass element. In terms of tangential and radial components, the tangential velocity is the product of the angular velocity and the radius. The tangential acceleration is the product of the angular acceleration and the radius. These concepts help us understand the dynamics of rotating objects, such as wheels and gears. Let's discuss the key angular quantities involved in fixed axis rotation. Angular displacement, theta. This is the angle through which a point or line has been rotated in a specified sense about a specified axis. The equation for angular displacement is the integral of angular velocity over time. Angular velocity, omega. This is the rate of change of angular displacement and is a vector quantity. The equation for angular velocity is the integral of angular acceleration over time. Angular acceleration, alpha. This is the rate of change of angular velocity with time. The equation for angular acceleration is the derivative of angular velocity with respect to time. These quantities are crucial for understanding the rotational motion of rigid bodies around a fixed axis. Let's delve into the concept of energy in rotation. When a rigid body rotates about a fixed axis, it possesses rotational kinetic energy. The formula for this energy is given by rotational kinetic energy equals 1/2 times the moment of inertia times the square of the angular velocity. Here, the moment of inertia is a measure of how much resistance an object has to rotational motion, and the angular velocity is how fast the object is spinning. Examples of fixed-axis rotation include rotating wheels, ceiling fans, a spinning disk where torque causes angular acceleration, and rotating gears in machinery. These examples show how rotational kinetic energy plays a crucial role in various mechanical and everyday applications. Let's discuss general plane motion. This motion combines translational and rotational movement. An example is a rolling wheel, where every point on the wheel follows a circular path while the wheel itself translates forward. Key kinematic relations describe this motion, such as the velocity of a point on a rotating body. The equation is: the velocity of any point equals the velocity of the center of mass plus the cross product of angular velocity and the position vector relative to the center of mass. Understanding general plane motion is crucial in analyzing the movement of machinery parts and vehicles. In this deeper look at general plane motion, we need to consider both linear and angular components simultaneously. The key principle here is that we can analyze the motion by breaking it down into two parts: the motion of the center of mass and the rotation about the center of mass. This is known as the principle of superposition of motions. For instance, when analyzing a rolling ball down an inclined plane, we consider both its translational acceleration down the slope and its angular acceleration about its center. This combined analysis helps us understand complex scenarios like gear systems and mechanical linkages in machinery. The work-energy principle is a powerful tool in analyzing rigid body motion. This principle states that the work done by all forces acting on a body equals the change in its total kinetic energy. For rigid bodies, this includes both translational and rotational kinetic energies. Think of it like a bank account. The work done by forces is like deposits and withdrawals, while the kinetic energy is the balance. This principle is particularly useful when we're more interested in the overall energy changes rather than the detailed motion at each instant. When dealing with rigid bodies, kinetic energy takes on two forms: translational and rotational. The total kinetic energy is the sum of half mv square, translational, and half I omega square, rotational. This is beautifully demonstrated in a rolling ball. It has kinetic energy due to its forward motion and additional energy due to its spinning motion. This explains why a rolling ball travels farther than a sliding one. It has more total energy to dissipate. Understanding this dual nature of kinetic energy is crucial for designing efficient mechanical systems. Moving deeper into the work-energy principle, we examine how work is calculated. The work done by a force is given by the integral of F dr, where F is the force and dr is the displacement vector. In simpler terms, it's the product of force and displacement in the direction of the force. For rotational motion, we also consider the work done by torques, given by the integral of tau d theta, where tau is the torque and d theta is the angular displacement. This helps us analyze complex situations like cranes lifting and rotating loads. Let's discuss the conservation of energy. When no external dissipative forces, like friction, act on a system, the total mechanical energy remains constant. This is represented by the equation. The sum of the initial kinetic and potential energy equals the sum of the final kinetic and potential energy. This principle is crucial in various applications. For example, in an oscillating pendulum, the kinetic energy converts into potential energy and vice versa, demonstrating energy conservation. Similarly, in flywheels, energy analysis helps in understanding the energy storage and retrieval mechanisms. Understanding the conservation of energy is essential for analyzing and predicting the behavior of mechanical systems. Understanding rigid body kinetics is crucial in engineering applications. It helps determine the torque and energy requirements for the efficient functioning of gears and machinery, ensures cranes and lifts operate safely and efficiently under various loads, and aids in designing safer, more efficient transportation systems by analyzing vehicle dynamics. These applications highlight the importance of rigid body kinetics in solving real-world engineering problems. We have reached the end of this video today. Thank you for watching, and don't forget to like and subscribe for more tutorials on other exciting topics.